Hi there, Serdar Yegulalp here for InfoWorld at IDG. In this episode of SmartGo, I'm going to demonstrate Go's channel data type, a way to send and receive messages between Go routines. In an earlier video, I talked about Go routines, which are functions that run concurrently and are managed by the Go runtime, which makes them easy to work with. Channels let you pass data back and forth between Go routines, and are also managed entirely by the Go runtime. All you have to do is declare them and use them. Here's a simple example of how channels can work in Go. In this program, we have a channel that sends random integers from one Go routine to another and prints the result to the console. So to create a channel, we use the make keyword along with the type of object we're making, a channel in this case, and also the type of data to be sent through the channel. Channels require a data type. In this case, we're sending integers. We then refer to this channel with the variable CHN. Now, when we want to send and receive data in a channel, we use a syntax that uses a left-facing arrow. When we point the arrow at our channel variable, it sends a value into the channel. If we point the arrow away from the channel, it receives a value from the channel and stores it in a variable. Note that for each of these operations, we're invoking the functions that contain the send and receive as Go routines. The general rule is that you use channels in conjunction with Go routines, although there are cases where that's not an absolute requirement. It's just that the majority of the time that's the use case. You'll also note that I have a defer statement here with close. This closes the channel at the end of the function, no matter what happens. Once a channel is closed, it can't be written to anymore, although any pending messages still in it can be read. This will become more important later, as I'll demonstrate. If we run our example, you can see 5 send and 5 receive operations taking place, each one separated by a short, artificially imposed delay. That's just to make sure all the Go routines run to completion before going on to the next loop. But as you can see, each of the 5 values gets stored in the channel in one Go routine, and then all 5 get read back in another. Channels, by default, are bidirectional. You can both send and receive using them. But when you declare a channel type in a function signature, you can specify if the channel in question is to be only sent from or only received. And the syntax for this is similar to the syntax for sending and receiving itself. So here's a modified version of the previous example. In send and receives function signatures, we now have modified signatures that declare that the channel variable is to only be used for sending and receiving. Our program will still behave the same way because we haven't tried to do anything other than send or receive in those functions. Channels can also be buffered or unbuffered, meaning you can control how many messages can be inserted into a channel before the channel blocks and has to be read from to do anything further with it. By default, channels are unbuffered. They can only hold one object at a time for reading or writing. If you try to send on an unbuffered channel that hasn't been read from yet, the send process will block. Here's an example of this. I've modified our earlier example so that the receive function waits 2 seconds before receiving from the channel, and our main loop waits 3 seconds at the end for everything to conclude. Watch what happens when we run it. We first see the sending to and receiving from messages in the main loop. But we don't see the sent value message from the send routine until 2 seconds go by, and the same thing happens with the value received message. What's happening here is that when we perform the send, because there's nothing yet open to receive it, the send function blocks until something receives from it. Unbuffered channels have no storage capacity. Again, if there's nothing waiting to receive from a channel, the send operation will simply hold up there until something does to receive from it. If we want to modify this behavior, we can give a channel a capacity. That is, make it into a buffered channel. Here's the same example as before, only this time we have a channel with a capacity of 1. This time, when we run it, the sent value message shows up immediately. When we want to talk about how many items a buffered channel can hold, we call that the channel capacity. When we refer to how many items are actually in a channel at a given time, we call that the channel length. Here, I've modified our example a little further to list out capacity and length as we run it. For capacity, we use the cap function, and for length, we use the length function, or len. The results should be pretty self-evident. We've created a channel of capacity 2 with a length of 1 whenever there's something in it, and with a length of 0 when there's nothing in it. One more thing we can do with the channel is receive from it in a for loop. Here is our original example modified somewhat for this. We're creating a channel with a capacity of 5 and loading it with 5 messages. Note that we're not using a Go routine to load the channel. We're just using a regular function call. We're doing that synchronously so the channel will stay full. Next, we close the channel. You'll find out why in a second. And then kick off the receive go routine and wait 2 seconds for it to finish. Just as an aside, we've been using time sleep to wait for go routines to finish for the sake of this demo, but there are more elegant ways to wait for pending go routines to finish. They involve the use of Go's sync package, and that's something I will explore in a further video. So, in our receive go routine, we read from the channel by way of this for loop construction. This is basically a way of saying, loop over everything that comes out of the channel until the channel is empty and the channel is closed. So we read all 5 messages, process them, and then because the channel's closed and all the messages have been exhausted from it, we leave the loop and print the total. If we didn't have the channel closed, the loop would sit and wait for more messages to be put into it. That's actually a handy pattern to use when you want a Go routine that just consumes messages from a channel indefinitely. Now, strictly speaking, channels don't actually require Go routines. They just make it easier to work with them because channels are often used in asynchronous constructions. Here's a version of the same script without Go routines. Since everything happens in the same order anyway, and also without the artificial delays we put in to dramatize how these things work, but notice that we're doing this with a channel with a buffer, because otherwise this demonstration won't work correctly. It'll just hang indefinitely. So again, the idea behind a channel is to have a way to send and receive messages throughout a Go program, typically between Go routines. Channels aren't foolproof, and again, that's something to explore in a future video, but they greatly reduce the amount of effort needed to communicate between the asynchronous components of a Go application. That's it for this video. If you liked it, please leave a comment below. Don't forget to subscribe to the IDG Tech Talk channel on YouTube. And for more Smart Go and more Dev with Serdar, be sure to follow me on Facebook, YouTube, and Infoworld.com.